and in particular the Princeton Environmental Institute, or PEI. So given the spirit of Frank Taplin, it's particularly fitting that today's honoree and speaker is Dr. Jane Lubchenco. Jane is the Undersecretary of Commerce for Oceans and Atmosphere and the Administrator of the National Oceanic and Atmospheric Administration, or NOAA. Jane is the first scientist and the first woman to hold this position. She comes from a background in marine ecology, but has, throughout her career, always understood and always worked towards the idea of bringing scientific understanding closer together with environmental policy. Her publications many of them are citation classics. She's a member of the National Academy of Sciences. She's a member of the American Academy of Arts and Sciences, and she's received numerous awards, including a MacArthur Genius Fellowship. And many of us know Jane very well and for a long time, and there's a nice Princeton connection in that we've had the pleasure of having her son in our PhD program, and we even graduated him, which reflects hopefully well on us. So on a more serious note, Jane has experienced, and many of you know this, experienced and had to deal with a number of challenges since taking office. And I wanted to give you an example of her remarkable leadership by highlighting something that you may not be familiar with, because in a way it's been under the radar screen, at least relative to national emergencies, but nevertheless is of exceptional importance. She and her staff have traveled the nation to visit town halls and to meet with fishermen and their families firsthand. And as a result, she's been able to forge an unprecedented agreement on catch limits of sensitive fisheries throughout our nation. And that is one of the greatest environmental issues confronting us today. And in an editorial, this is from January 20th, this is an editorial from the New York Times and was devoted entirely to this agreement. The New York Times referred to this as a historical agreement that is fully supported in a bipartisan manner, which is a great success. So this is very much in the spirit, I think, of Frank Taplin and of this lecture series. So we're so delighted to have you here today, Jane. It's my great pleasure to introduce you and your topic, which is creative solutions at the interface of science and policy.
Thank you very much for that, Lars. It's a great pleasure to be back on campus. Thank you, everyone, for coming today. I know I'm competing with Bill Bradley, so I'm delighted that I have a full house here. Thank you for that. I want to tell you a story today. And the story begins, my last name is Ukrainian, Lubchenco. Many people have trouble saying Lubchenco, and in fact, Simon is one of the best champions I have for the correct pronunciation of my name. But when I went to NOAA, people were skittish about saying it wrong, so they started calling me Dr. Jane. So I'm Dr. Jane, and this is sort of a story of Dr. Jane goes to Washington. What I want to do today is tell you a little bit about what I've discovered about the very cool science that NOAA does and that NOAA funds academics to do, how this science saves lives, benefits the economy, protects human health, protects food security, contributes to national security, and promotes healthy oceans and coasts, and how the landscape for this science is changing very dramatically at the time when we need this kind of science now more than ever before. This kind of science I call use-inspired science, and I will come back to that term a little bit later. But I want to really focus your attention on and enlist your aid in promoting the importance of use-inspired science. So NOAA is, first and foremost, a science agency. Its roots actually go back to the very first science agency in the United States. 1807, President Thomas Jefferson created the Survey of the Coast because he understood how important it was to have adequate scientific information for maps and charts to both enable national defense, but also commerce. Fast forward 1870, the Weather Bureau was created. 1871, the Bureau of Commercial Fisheries. So those independent scientific service provision functions, grounded in science, were created in 1970 under Richard Nixon. They were all brought together under what was a very innovative, very forward-looking concept at the time of Earth system science, even though nobody called it that. But the idea of bringing together an agency that had responsibility for oceans and atmosphere, the science of oceans and atmosphere, was a pretty revolutionary idea at the time. We don't think anything of Earth system science today, but at the time it really was cutting edge. And in truth, NOAA was very stovepiped. The different parts that were sort of cobbled together in this creature remain stovepiped for some time, but they are not anymore. That integration across oceans, coasts, weather, climate, fisheries, and the science that underpins those is very much obvious and in service to society. So NOAA is a science agency. Our responsibilities are to provide services. Most of you are very familiar with the National Weather Service and what it provides, but also nautical maps and charts. We also have stewardship responsibility for oceans and coasts, fisheries, protected species like whales, other endangered species, turtles, etc. This Earth system approach to science is very much what we are all about. Not just understanding how systems work, but being able to provide useful information to enable people to make decisions. So we do observations and predictions. Those observations are everything from our weather satellites to ground-based observations, a lot of ship-based information. Conservation and management, research and education are sort of three major bins of what we do at NOAA. And this integration across the different parts of NOAA, but across the different elements of Earth system science, biogeophysical, socioeconomic, really are in support of national and homeland security. When the Department of Homeland Security was created, there were some primary functions of government that were described as being essential. So if the government is threatened for whatever reason, what are the things that we have to keep going? And NOAA, in fact, has two what are called primary mission essential functions. One of them, and we call them critical environmental intelligence. One of them is to collect and provide the nation with intelligence, data, imagery, and other essential information for predictive environmental and atmospheric modeling systems and space-based distress alert systems by operating NOAA-controlled satellites, communications equipment, and associated systems. So that's one primary mission essential function. The other is to provide the nation with environmental forecasts, warnings, data, and expertise critical to public safety, disaster preparedness, all hazards response and recovery, the national transportation system, safe navigation, and the protection of the nation's critical infrastructure and natural resources. So even from the lens, most of you would not normally think of NOAA as something having to do with homeland security and national defense, but I'm emphasizing that, in fact, its portfolio touches a lot of different elements of what is important to the nation. A lot of what we do is also in direct support of the economy. The maritime commerce industry is over $700 billion a year. The National Weather Service provides critical information for the aviation industry, for the transportation industry, et cetera. Fisheries are economically very important, as well as from a food security standpoint. And then, of course, information about climate and what we might expect down the road. It's helping to inform our understanding, not just of what's happening now, what's happened in the past, but what might happen in the future. Our stewardship responsibilities loom large. I mentioned those earlier. But healthy oceans and coasts also have benefits for human health in terms of preventing things like harmful algal blooms, enabling healthy seafood as an important part of diets. So across all those different parts of, this is part of what we do at NOAA, is science in support of a lot of the things that people take for granted and may not in fact know are part of our mission. We also are called upon to respond to crises during Deepwater Horizon or the Japanese tsunami in particular, but also the radiation disaster. The science that we do in-house and that we enable through cooperative institutes or grants to academics underpins this mission. And this is, and I'm emphasizing this because I really want to draw a line under the importance of use-inspired science as a legitimate, valid category that is worth understanding and supporting. NOAA scientists have identified a number of big challenges that they think are directly in support of our mission that we need to tackle head-on. These are listed in this slide here. I'm not going to read them. But addressing grand societal challenges, be it climate change or food security, really requires fundamental advances in understanding. Advances that are pushing the cutting edge of knowledge, but are also immediately relevant to society's problems. And the ones that are really highlighted here focus on human behavior and the nexus between social sciences and natural sciences. They focus on the interactions between atmospheric composition and climate variability and change, on the interaction between climate change and oceans and how we should be thinking about managing fisheries, understanding more about ecosystem processes and the multiple environmental changes that are underway that affect the functioning of ecosystems and therefore the delivery of ecosystem services. So not just through a fisheries lens, but through the lens of understanding all the different changes underway. How do we fold that into our management decisions? How do we fold that into policy to help us think not just about managing for today, but managing for tomorrow? And of course, the water cycle looms large as an area where we really need a lot more information. So that gives you sort of a broad purview of some of the topics and some of the areas, some of the cutting edge research that we are engaged in and wanting to tackle. And what I'd like to do is give you a number of specific examples where science has enabled us to do a better job in providing services or being better stewards, and what some of the cutting edge areas are, more topical by topical area. So I'll start with weather. The National Weather Service is a very important part of NOAA. We have responsibilities for helping to save lives and property through not just routine weather forecasts, but disaster warnings. That's part of our core mission. This requires integration of information from satellites to ground-based systems. So observations, and in fact, you may be surprised to know that over 90% of the data that go into our numerical weather models come from satellites. So those geostationary and polar orbiting satellites, our weather satellites that are up there, are actually really, really important for our ability to deliver weather services. So these observations, understanding of the dynamics of weather systems, the actual mechanics, the physics of it, and understanding and being able to assimilate data into models, run the models, and do forecasts. All of those are required for this. We are, so that's sort of the context. In the process of doing weather forecasts and disaster warnings, we track lots and lots of different kinds of things. One of the things that we track are the number of disasters each year that total at least $1 billion in damage. Guess how many we would have in a normal year? Any ideas? How many disasters over the last 20, 30 years, on average, how many disasters that would total over $1 billion? 3, 4, about that number. What do you think the record was until 2011? There were 9, at least $1 billion disasters set in 2008. We had a lot of hurricanes that year. Last year, 2011, we had 14 at least $1 billion disasters, and they were across every different possible category of weather, from hurricanes to tornadoes, from floods to droughts, from wildfires to whatever else I'm missing. Blizzards, big storm blizzards. So every single category. You see those listed here. These are the 14. You can look at those. And obviously a lot of people are saying, why, what's going on? This is important to note that this is this is the amount of, so these are a reflection of the economic damage that was created. It's probably a combination of increased number of events, plus more people in harm's way, more people with stuff that's insured, and again, more people in vulnerable areas. So it is conflating all of those. So you can't draw a conclusion that says, aha, climate change is happening, for example. You know, so I just want to put this in context and make sure that it's not being misunderstood. So this does raise the question, though, how do we do a better job of incorporating understanding of the climate system, both climate variability and climate change, into our ability to do forecasts if, in fact, we are going to be seeing increasingly large number of very devastating events. Equally importantly, how do we do a better job of warning people and keeping them out of harm's way to the extent that you can? So both of those are important. I want to focus on the former and really the science of detection, attribution, and prediction. And focus on climate models for a moment. And I had the pleasure of spending a few hours this morning at NOAA's science laboratory at GFDL and meeting with some of the really outstanding scientists there and learning a little bit about some of the things that they're working on. And one of these actually relates directly to this topic. And the need is to have higher resolution models, but also more complete understanding so that we can account for all the components, not just, so for example, the carbon cycle. That's a new area of research. So Earth system modeling and the GFDL scientists have completed a new multi-century control simulation and an idealized climate change simulation using a new high-resolution coupled climate model called CM 2.5. These high-resolution models ultimately will allow us to simulate aspects of climate variability and change on regional spatial scales. And of course, that scale, that regional scale, is of keen interest. So this is an area where cutting-edge science is actually enabling us to do, or will enable us to refine and do a better job of the kinds of responsibilities that we have. So one of these events you'll see was Hurricane Irene, and I want to dig a little bit deeper into one of these for a moment. Hurricane Irene, I think, is a nice example of where an investment in science has really paid off in our ability to do a better job. It's a little bit easier to forecast hurricanes than it is to answer the question, how is climate change going to affect a lot of these extreme events? That's way far down the road. But an investment in understanding the physics of hurricanes has paid off in spades in enabling us to get better and better and better at forecasting where a hurricane will go, the track of a hurricane. And I'm going to show you an animation of Hurricane Irene. You will see the hurricane coming across the Atlantic, heading for the coast of Florida. You will see the forecast track, and then you'll see overlaid on that where Hurricane Irene went. So let me start the animation here. Here comes Irene, and 5 days out, this was the forecast that we made about the track that would follow, and she was right smack on that track. That's pretty darn impressive. And that's what an investment in science can do for you. You can get better and better at things like this. So the track errors have been cut in half over the past 15 years. A 10-year track improvement, so it's as accurate at 48 hours now as it was 24 hours in 1999. We have not done an equally good job of improving the accuracy of the forecast about intensity of the hurricane. So where it will go, we've got nailed. How intense it will be, whether it'll go from a category 2 to 3 to 4 to 5 or get downgraded, that's a lot more complicated. And we are now in the 4th year of a 10-year project called Hurricane Forecast Improvement Project that is designed to better understand the dynamics, get the data. This is what our hurricane hunter planes and scientists do. They fly through hurricanes, they get those data. You have to assimilate those data, you have to have the models. And so this is an area where we have staked out that is increasingly important for us to understand. And we saw that with Irene because we didn't get the intensity right. And intensity is really important because that's what determines storm surge. So this is 2 examples with hurricanes where we've done a really good job with investment in science, another where we have more work to be done. Craig Fugate has pointed out, he's the director of FEMA, that with the track of Irene, as it was 5 days out, 10 years ago, we would have had to evacuate the entire east coast of Florida. We did not do that for Hurricane Irene because the model said, no, Irene's not going to hit Florida. She's going to go up and hit the Outer Banks, and lo and behold, that's exactly what happened. So the avoided evacuation, the economic benefits of avoided evacuation are very significant. So there's direct benefit from this. Okay, so this is part of what the Hurricane Forecast Improvement Project is designed to do for anybody who wants a little more granularity in terms of what actually is underway. I'm not going to go through that, but there are a number of different aspects that are both the models, the actual physics, the data assimilation, et cetera. Let's go back out to a larger scale again, and I want to just point out that there is wide variability in our understanding of many of these different phenomena, all those different categories of weather that I mentioned earlier. This slide is based on a published figure but hasn't been published in this form. The x-axis here, and listen to this carefully because this is a little complicated. The x-axis is how good is our understanding of the factors that are responsible for long-term changes in the frequency and intensity of extremes within any one of those categories. So let me say that again. How good is our understanding of the factors responsible for the long-term changes in frequency and intensity of extremes with, let's say, heat waves or ice storms? The x-axis is how adequate is our ability to detect changes and trends in those extremes. And you can see that we're sort of all over the map here. For example, we have a relatively good understanding of what can lead to changes in heat waves. We understand that pretty well. And our data are fairly adequate to detect those changes through time. So that's sort of at one end of the spectrum. At the other end, ice storms, both our physical understanding of what factors influence their prevalence and the data on their frequency and intensity are inadequate. So this is to give you a sense of the richness of the problems from a very simple standpoint of how much we understand it and how good our data are to detect the kind of changes we might be looking for. And again, we're really focusing on extremes in these patterns. So I just thought that would be an interesting thing to show you. Narrowing down now for just one more example on an area where we do have a lot of good data, and that's temperatures. This slide focuses on warm minimum temperatures. So obviously there are some environmental variables for which we have lots of data, and you can begin to have a more robust understanding of changes. This particular figure is from unpublished work that's in process from Rick Katz, who's at UCAR, and he's a co-author on 3 papers with some of the NOAA scientists where we've been looking at changes like this in support of the National Climate Assessment. For the National Climate Assessment, we've been having workshops, and these are papers that are feeding into this. This figure shows the percent of the area of the US that experienced warm minimum temperatures through time. And it starts in 1910 and goes through 2010. The blue line is a smoothed version, it's a binomial filter, of the annual, which are the black bars, and the red line is a non-parametric trend analysis. So this gives you a sense of what the changes are in the pattern of warm minimum temperatures. Another example that is relevant from an economic standpoint is the ways in which different types of extreme weather events have disturbed the electrical grid. So we don't have data on all the ice storms or other things, but we do have good data on events which have caused some major disturbance in the electrical grid. So from the 2009 impacts report of the climate assessment, that's what this figure is from. This is the number of incidents caused by extreme weather. They increased tenfold between 1992 and 2008. So the data that are shown here include disturbances that occurred on the nation's, so this is the bulk electrical transmission systems. And it just highlights the increasing impacts that extreme weather events can have on just one part of our economic system. And it really underscores the need for more comprehensive and robust monitoring of different key types of events. So that's a smattering of different examples sort of in the weather and the climate world that give you a sense of some of how investments in science are paying off and what some of the areas where we see of research being needed. I'm going to switch over to oceans now for a moment and begin with a focus on ocean acidification. Areas, the oceans absorb carbon dioxide from the atmosphere. They're 30% more acidic than they were at the beginning of the Industrial Revolution. And the pattern of acidification is not playing out equally every place. This figure shows along the west coast of the US, at the surface on the left and at 125 meters on the right, where you see increasing acidification, especially as it is brought to the surface through upwelling events. And so the hotter red areas at the surface are more acidic waters that are being brought up from depth and are in fact already impacting many species along the west coast. The chemistry of this is fairly well understood. What we don't have a good handle on is the spatial and temporal variability in the changes and what the biological and ecological and social consequences of these changes are. We do know that many species that make shells or skeletons of calcium carbonate are affected, but so too are a variety of basic physiological processes. For example, the ability of fish to smell. So salmon being able to find their natal streams, or anemone Nemo fish being able to detect predators so they can dive into the tentacles of anemones, is strongly affected by changes in ocean acidification. One of the very practical benefits of the research that has been conducted on ocean acidification is playing out along the West Coast with the oyster industry, which is significant in economic terms and in terms of jobs. West Coast upwelling associated with changes in aragonite saturation and in pH are directly impacting the oyster hatchery industry. This oyster hatchery, the shellfish industry, to give you a sense of it, is the shellfish industry on the West Coast is about $111 million per year. Probably about 80 million of that is oysters. It's about 3,000 jobs. So that sort of gives some of the social context. What the scientists who were studying this discovered is that when these upwelling events happen, the more acidic water kills the larvae, essentially. And so in the oyster hatcheries, what they have begun doing is having monitoring stations that give them a sense of when upwelling is happening, and then they cannot use water in the hatchery from that particular time, and they will wait. The upwelling in this system is intermittent, so they will wait until it's not upwelling, and then they can use the water in the hatchery. So there's been a very immediate direct benefit that has been a short-term solution for this problem, not certainly a long-term solution. NOAA is the lead agency across many of the federal agencies on research and monitoring in ocean acidification, and we work really closely with many of our academic partners that are funded not only through NOAA but through NSF and other grants. And this is an area where I think there is a lot more research that's needed to truly understand what are the consequences, how we can be folding that into management practices. So I want to segue from there to fisheries and talk a little bit about climate changes in fisheries. Food security looms large. A lot of people think only of land when they think about food security. I want you to always think about oceans as well whenever you hear the word food security. When you consider that about 2.5 billion people depend on seafood for their sole or primary source of protein, it gives you a sense of how important fisheries is globally. The challenges to sustainable fisheries loom large, but the problem is even more complicated in an era of climate change and then ocean acidification. And we are already seeing shifts in species distributions. What you see here is a commercially important species, silver hake, just as an example of some of these shifts. And you can see in the distribution 68 to 72 on the left, and then 2003 to 2008 on the right. Silver hake is moving northward. In the Northeast, 2/3 of the 36 fish stocks that were examined shifted northward and or deeper, so both of those are happening over a 40-year time period. In the Bering Sea, fish have moved northward as ice cover is reduced and the amount of cold water from melting sea ice is reduced. In both of those cases, fishermen are having to travel farther and set their nets deeper, and so, of course, that increases the costs associated with fishing. And one interesting recent study found in the California current large marine ecosystem that shifts in spatial distribution were more dramatic for species that were heavily fished or overfished. So it really points to the nexus of climate interactions with fishing practices. So combining these studies really underscores the importance of good fishery management today, but the importance of managing fisheries not just for today, but for tomorrow. And what does that mean? How should we be doing that? And it's not just individual species responses, but trophic interactions, food web interactions, how prey is being affected, and all of that is a very cutting-edge area. Many of the scientists at GFDL are working closely with Princeton scientists looking at some of these interactions, how using climate models to get a better sense of what fisheries impacts might be and ecosystem impacts might be. So that's very cutting-edge research that is immediately relevant to the kind of policy and management decisions. It also underscores the importance of managing fisheries well and changing the incentives in fisheries. And one of the things that we've been doing at NOAA is really listening to the science that is out there about management and how we can do a better job of managing fisheries sustainably. And in this case, utilizing rights-based management tools such as catch shares to align conservation and economic incentives. And this is an area where we have been making progress and will continue to do so. In addition to the sort of normal responsibilities that we have and the science that underpins those, when crises happen, like Deepwater Horizon, much of the science that is done at NOAA or supported by NOAA is immediately directly relevant to a response effort, and that was indeed the case with Deepwater Horizon. We had responsibilities for not just doing weather forecasts, spot weather forecasts to do the day-to-day operations, but detecting where the oil is, modeling where it will go the next 24, 48, 72 hours based on oceanographic and weather models. Protecting species and habitat, especially species that are protected species, turtles, marine mammals. Protecting the integrity of the seafood by closing fisheries, any place there was oil or we thought there would be oil. And then developing new methodologies to test for the presence of not only polycyclic aromatic hydrocarbons, PAHs, but also dispersant, so that we could, in good conscience, open areas back to fishing when in fact it was appropriate to do so. NOAA scientists started taking data on what impact is the spill having on about day 3 of the event and are still taking data on impact, are preparing the court case against the responsible parties as part of the natural resources damage assessment process that is designed by law to focus on what was the damage done to natural resources and the public's access to those natural resources, and then what restoration is appropriate to compensate for that damage. So that process continues. The immediate response is over, but the impact assessment and the restoration efforts are continuing. I think it's fair to say that there was a lot of new, novel, actually pretty cool research that was done during the spill. But it's also true to say that in many ways our knowledge of how oil behaves in water and how to do effective cleanup had not really advanced since the Exxon Valdez. And that's an area where we really need a lot better and more research, especially as we are beginning to explore possibilities of drilling in Arctic waters, where behavior of oil in very, very frigid waters is going to be quite different from what it was in the Gulf of Mexico. Some of the surprises that came to light during Deepwater Horizon were how very, very rapidly microbes that we didn't even know existed were mobilized and essentially consumed much of the oil. We learned a lot about the loop current, which in fact was a very lucky situation. The loop current is a current of warm water that comes up between the Yucatan Peninsula and Cuba, goes into the Gulf of Mexico, forms a loop, turns around, and then goes back out through the Florida Strait. And if it had been in its very loopy form, could in fact, excuse me, have acted as a conveyor belt of oil to the Florida Keys and then into the Gulf Stream. Luckily, the top of that loop pinched off into what was called Eddy Franklin, named after Benjamin Franklin, who actually first identified the loop current, among other things. And because it pinched off, it was not a mechanism for transporting oil away from the Gulf. So there were a lot of things where we actually lucked out in that. We can't count on that for other events, but we learned a lot. Another quick thing that we learned that's actually pretty cool, many of the air chemists, atmospheric chemists, were interested in what kind of signals could they detect about the oil that was flowing from more than a mile down by sampling air. And they actually have figured out, you will all remember, I suspect, that there was a lot of controversy about what the flow rate is, how much oil was being released. Well, and one of the challenges was we couldn't measure directly what the flow rate was, and so people were having to go through a lot of indirect ways to get that information. Well, one cheaper and turns out very good way is to sample the air above the, in this case, above the Gulf, and you could have calculated flow rates based on the air chemistry, which is actually pretty interesting and pretty cool. Okay, so enough on Deepwater Horizon. I could talk about that for a long time, but I'm not going to. One other crisis that we were intimately involved in that drew on science and pushed us to develop some new things is understanding of where the debris field that was washed into the Pacific in the aftermath of the 3/11 earthquake and then tsunami in Japan, where that debris field is and will go. And the initial models that were predicting where will it go were based on climatologies. What are the average conditions? Turns out that they were actually about, they were way off. They underestimated where the debris field would go for two reasons. One, this was not an average year. And once there were real-time data, HICOM data from Navy models that could be incorporated into a new model that our folks generated, we could do hindcast to say, okay, given the actual real-time currents and winds, where should the stuff be now? So we've changed the models to do that. And secondly, taking into account not just ocean currents, but windage. So something that sits low in the water is going to be transported primarily by ocean currents. Something that sits up high, like a buoy, for example, or a fishing vessel, where the wind is pushing it faster than the currents might, is going to travel faster. So the figure that you see here is a model that incorporates these new data, and I have to come over here because I can't see it from down there. So this is through April 7th, and this is a model that seeds where the event happened with particles, and then has used the real-time oceanographic and atmospheric data between when it was released and now to say where is it now as of 4/11. And so this is probabilistic. It says the bulk of the stuff is here. These are the Hawaiian Islands. So this is north of the Northwest Hawaiian Islands. But some of the stuff that is carried very, very rapidly by winds, according to this model, would have reached the West Coast in December, January, February. And in fact, that's exactly what we're seeing. So the original models said that the first stuff won't hit until a year from now in terms of the West Coast, and it's hitting now. So that new model is actually helping us better understand transport in events like this and the importance of not using only climatologies. Okay, finally, I want to just focus on the importance of biodiversity and getting more information about what's in the oceans and how it behaves. This is an area where I think we have not done anywhere near as much work as we need to. The Census of Marine Life really highlighted some of the possibilities there and how much is not yet known. And as we are thinking about challenges, this one certainly looms large. So I want to segue very quickly now to begin to wrap up by focusing your attention on the kinds of cutting-edge use-inspired science that I've been describing, and I've only touched the surface here. Climate change and adaptation, extreme weather and water events, healthy oceans, sustainable fisheries are all really important there. But what we're seeing as that science becomes more and more important is less and less of an appetite to fund that kind of science. And I would draw your attention to an article that was in Nature, Dan Sarowitz, in January, where he says, as the current budget crisis unfolds, the erosion of mission-oriented research is likely to accelerate. If you look at the actual funding patterns, and this was an article that was in Science that same week, January 2012, you look at the funding patterns. This is percentage changes from 2010 to 2012 in billions of dollars. And you can see on the right-hand side, the agencies that are doing well. NSF obviously is doing well. NASA, DOD, NIST, USDA. NIH is doing pretty well. DOE is doing pretty well. So those are both basic science, like NSF, but also what I would call use-inspired science agencies, but in the area of energy or in the area of health, for example, and NIH is clearly the strong example. The agencies whose science is not doing as well are environmental science agencies, such as NOAA, USGS, and I think it's that area where it is appropriate to have a dialogue about the social value of that research. And I actually think that it's appropriate to begin the dialogue by thinking about the mental model we have about science and the model that Vannevar Bush proposed, which is a very linear model. And I certainly, as a young scientist, grew up being told you have to choose between doing basic science and applied science. And it was sort of one or the other. There's sort of two choices that are out there. And in fact, I think I am much more compelled by Donald Stokes' model, and in particular by Pasteur's quadrant, where he's drawing attention to use-inspired science. In other words, cutting edge, really pushing the boundaries of knowledge, but that is directly relevant to societal problems. That is distinct from what NSF funds, which is really blue sky, curiosity-driven, cool stuff. And in my view, we need both of those, but we have not really made the case for the importance of use-inspired science. And I think when Vannevar Bush framed his ideas, the assumption was applied science is so obviously relevant, you don't need to make the case for it. You need to make the case for basic science, because that's what's hard to sell to government funders. I think that there is a dialogue that we need to happen that is really focusing on not just basic versus applied, but use-inspired science, not only done by government agencies, but funded by them, but that is creating the knowledge that we need to be grappling with a lot of these social problems. Now, NIH has made that case. They don't call it use-inspired. They call it translational science. We haven't made a comparable case for environmental sciences, and I think we need to, because the pressures that are on our budgets are very, very intense. And much of the important work that I've described and much that we're not yet able to do is not going to happen unless we can make a better case for this. So again, cutting-edge, use-inspired science of the kinds I've been describing, I believe, are incredibly important, and they are greatly at risk right now. In addition to doing science, I think it's also important to strengthen the capacity within agencies to do use-inspired science and to protect the integrity of the science. And so in closing, I want to just tell you about some of the steps that we have taken at NOAA to create a new policy on scientific integrity consistent with the President's direction that I believe is a really spectacular policy that forbids misusing, suppressing, or distorting science, but also enabling scientists to talk freely to the media without having to go through gatekeepers, and to do things to strengthen science. I have talked about some of what NOAA's portfolio is, some of our successes and opportunities, some of the policy challenges that I see, how I think we need to reframe scientific research to really create some legitimacy for use-inspired science. Lou Branscombe uses the term Jeffersonian science. NIH calls it translational science. Whatever we call it, I think we need to have more emphasis on the legitimacy of that. When I talk to members of Congress about science, they say, well, we're funding NSF. Check that box. We've done science. They've bought into that, and they think it's important. And my pitch would be, yes, it's vitally important. We need NSF. We also need use-inspired science that the mission agencies are doing. We also need to be cognizant of the pressures on science and scientists and rationality and fact-based decision-making that is part of the larger social dialogue that is underway, because that's part of this, challenge that we all have. So Dr. Jane Goes to Washington has been a really fun, rich experience. I've been greatly, greatly impressed by the caliber of the science, but also by how important it is to our nation. And I'm just delighted to have been able to serve as administrator and to be part of what I think is a really impressive agency. We tell members of Congress, if I had a nickel, I would hold it up, that it costs less than 5 cents for every American, less than 5 cents a day for each American to fund all of what NOAA provides for the nation. And I think it's a pretty good deal. So this is not a pitch for NOAA, I know it sounds like it, but it's really an invitation to help us think about the role of science in our society and how important use-inspired science is in addition to basic science. We need that full depth, we need that full richness, we all benefit from it, and we need to make sure that it doesn't fall by the wayside. Thank you very much. Thank you.
That's terrific.
Thank you.
Can we take questions?
Sure.
Yeah. Yep. Thanks, Jane, for a terrific and informative talk. We have microphones set up for questions, and there are 2 ways you can do it. Either if you're close to go down, you can come down. Otherwise, I think we can also run up to you and hand you the microphone. But please use the microphones.
Thank you very much. When you talked about the atmosphere, you talked basically about the troposphere, the lower atmosphere. Is NOAA concerned with the upper atmosphere, ionosphere, magnetosphere, solar radiation, solar storms? You mentioned the electrical grid. Of course, one of the causes of malfunction of the grid is solar flares. So I wonder what the A in NOAA stands for. Thank you.
Thank you for that question. It's all of the above. I, frankly, before I went to NOAA, didn't even know there was space weather. But indeed there is, as you are obviously well aware. One of NOAA's responsibilities is to forecast solar events. We have the Space Weather Prediction Center that's based in Boulder. And we work closely with both the academic community and other federal agencies in not only detecting but trying to warn when there are some kinds of electromagnetic radiation headed our way. And that phenomenon, I think, is very timely as we are entering or ramping up to another solar maximum. It is very important. I think likely we will see increased number of events, although we can have big ones anytime, as is fairly well known. So we have a small team that's doing that. It is not as many. Ram, would you say, how many scientists would you say we have that are working on that relative to lower atmosphere problems? Can you take a guess at that?
I can't say a number, probably less, but quite a sufficient number working on all parts of the atmosphere.
So some of our, some of those folks are working on climate parts of that problem. Others are solar weather. But good question. Scott?
Hey, can I ask you to identify yourself before you ask the question? Thank you.
Yes, Scott McVeigh, a graduate of this institution and a grateful recipient of a fabulous talk. Thank you so much. You brought up the matter of marine debris after the terrible tsunami earthquake from Japan, but I wondered if you might comment for a few moments on the extent, depth, and impact of that great mass of debris, a lot of plastic stuff out in the Pacific Ocean. And I wondered how you thought about the scale of it, what's happening to it, what the deleterious effects of it are, and what conceivably we might be able to do.
Tough question, Scott. Thank you. Some of the marine debris that was washed in after the tsunami is wood, buildings and stuff like that. Much of that will likely biodegrade. Some of it is likely, first of all, what was washed in was a pretty concentrated mass. Most of that sunk, and what is left has really spread out, and so you can no longer see it from space. For us to see it from satellites, we have to identify an area and really zoom in, and you can't do that at all places all the time. So it's not as if, even with the figures here, they were stippled, but it still looks like there's a big mass. I want everybody to understand that it's actually very, very dispersed. Some of that is likely to, the model suggests that it will continue to come across, hit the West Coast, come back around, and much of it, in fact, will end up in that Pacific gyre of which you were speaking. It has been accumulating stuff for a long, long time. And as you are well aware, when stuff doesn't biodegrade easily, like a lot of plastics, then it has a very, very long residence time there and is potentially very significant and very problematic for a number of species in ways that we frankly don't really understand completely. Physically clogging filters of filter feeders, yes, but the impact of the plastic compounds themselves, if they're ingested or if they're absorbed, I think we just, people are beginning to look at that, and I think it is a huge problem that we don't completely understand. Yes?
Thank you. My name is David Mattson. I'm a graduate of another Ivy League institution founded by Benjamin Franklin, and a concerned citizen. I want to tell you that as a business person, your presentation is well done and makes your points, particularly about the economic benefits of your work, clearly, from my experience. I was struck by a couple of things, and I wanted to ask you about policy. You mentioned the impact on the electric grid, which has become more pronounced, particularly as that electric grid ages, and also the deep water horizon, which initially happened because of a lax oversight of the people doing the drilling and the malfunctioning of a protective device that was supposed to cap that well, which suggests that there's some relationship in your science on the after effects of weather on infrastructure and industries. And I wondered, in terms of maximizing the research, the practical research, if anything's been identified with the oil industry or the electric power industry, or and I saw it also with the fisheries industry, to combine your research with other policies in those areas, and if so, would you elaborate beyond fisheries of what seems to be hopeful? Thank you.
So is your question focused on the impacts of a lot of these things that are happening on infrastructure in particular?
Where there are policy opportunities from an allied industry to work together with your agency to make helpful progress in prevention as well as, say, detection.
Right, okay. So we actually work closely with lots of different types of industries in different ways, not surprisingly. But let's return to the space weather example. The electrical industry is very concerned about the potential for significant disruption of the grid with a very significant solar event. I think a National Academy study of a number of years ago suggested that there could be $4 trillion worth of damage and 10-year recovery period for a really, really major event. So it's that scale. Nobody knows if that will happen or when, but it is possible. And I think one major point is that our technological society is much more vulnerable now than it was in earlier times when we have had significant solar activity. And that vulnerability underscores the importance of having some kinds of mechanisms to react if, in fact, we have warning that there is electromagnetic radiation headed toward Earth. That's part of what our Space Weather Prediction Center in Boulder does, is send out alerts when something is coming. There's a lot of discussion underway in the electric grid industry about what could be done to harden the grid against those kinds of things, what can be done to shut it down. Apart from that industry, communications could possibly be significantly impacted. Many of the communication satellites that provide everything from timestamp for financial transactions, GPS information for all sorts of things. Many of the private satellites, the companies know, but the public doesn't know if they can be shielded against solar energy or not. All of the government satellites are shielded, but that costs extra money. So we are actually in dialogue with satellite companies to talk about what they need to do, and then they make decisions about whether to do it or not based on their cost-benefit analysis about how likely it is. So we do, in fact, work with a lot of different industries on a lot of different fronts to provide the kind of information that they can use to then make decisions about being prepared for and responding to events when they happen.
That's hard.
Not enough, but we do some.
More questions?
I'm okay.
My name is Robert Cohan. I teach politics at the Woodrow Wilson School. And I had it was a great talk. I have a comment, and then a question. The comment is that you mentioned Donald E. Stokes' book, Pasteur's Quadrant. Don Stokes was dean of this school for 18 years.
Indeed.
Yeah, very distinguished political scientist. Some people in the room don't know that probably. Stokes Library is named after him, so we should remember his memory when we're
Thank you for
discussing
mentioning
it.
that, yes.
So my question is, goes to the point you made early about human behavior. What are the most important unresolved questions about human behavior that you're studying at NOAA?
So I'm going to bring that home to weather and give you a little bit of information. I told you how we had had a significant investment in our ability to give earlier and early warnings about events that were happening. Not just hurricanes, but tornadoes, severe storms. And we have, in fact, gotten better and better and better at doing that. And that is both an investment in science and in technology. The challenge comes when you have a 5-day heads up to Alabama or Missouri that says conditions are developing where we're going to have really bad thunderstorms, really bad tornado potential, get ready. 3 days, 2 days, 1 day. And then, you can't actually say a tornado is coming your way until it touches down. But the warning time, the average warning time is between 14 and 25 minutes, depending on which of those tornadoes it was. That's not a lot of warning time, but if you have a heads up, then you should at least be prepared and be thinking about it. So when we have a disaster like this, we go in and we do a service assessment afterward so we can figure out what worked, what didn't work, how can we do better next time. And what we learned in the service assessment from Taplin, Missouri, was that people had heard all those warnings, but they hadn't taken them seriously. And they knew the conditions were possible, but they didn't really pay much attention. And many people waited until they got a text message from their friend saying, hey, are you doing something? And so this is, I think, a perfect example of how human behavior, we need to understand human behavior better to be able to save more lives. Not that we can control what people do, but as a result of that experience, NOAA has launched a new program called Weather Ready Nation that is teaming up with social scientists to try to do a better understanding, try to understand better what people hear when they hear one of our warnings. Do they actually hear what we think we're telling them, or are they hearing something else? And what is it, do they know what to do? And at what point and with what information do they then take action? So we are testing, this is a new effort that is really engaging more social scientists to try to understand, in just this very specific circumstance, how can we do a better job of communicating, giving people the information? They still may not do anything, but at least we can be better informed about how to increase the likelihood that they're not going to die, essentially. And I think we're going to use that experience and as we talk about other problems, but that's just a very concrete one.
There are more questions here, but I'd like to take a brief break to let people leave, but before those who need to leave, before you do, we have a present for you here, a little thing.
Oh, how nice.
So thank you very much, Jane.
Thank you, Lars. Very nice. That's lovely. Thank you very much.
So please don't, if any of you need to leave, please leave, and we can continue some of this discussion. Terrific. You have a lot of questions. This is
Yeah, that's great.
This is great.
Yeah.
I think you stirred. There's
Well,
a lot
lots of different areas.
You're stirring a lot, but you're also stirring. You know, a lot of people here are motivated exactly by all these issues.